All right, so our next chapter is chapter 15, which is on fluid mechanics. So to understand what fluid is, so then we can study, let's say the dynamics of the, fluid, we need to understand that anything, like any matter, can be classified into one of these three states, or at least, the three states that we'll be considering. There's also a fourth state, which is plasma, which we will not be considering. But you can basically classify it as a solid, which has a definite volume and shape. So let's say, for example, like an ice cube, right? Something like this. And you have a liquid, has a definite volume, but not definite shape. So if you have a glass of water, so it has a definite volume, but not necessarily the shape. And then you can have you know, the same substance can be also in state of gas. Unconfined, has neither, a definite volume nor shape. So let's say you can have a container with, let's say water molecules in it. So they're just randomly moving, not keeping any shape, and doesn't have any size and things like this. All right. So that means what we're going to do here is we then going to be more or less using this general, let's say, three states of matter, right? And we're going to then talk about which one of those or combination of those then can be considered fluids, because all of those things are not necessarily, you can say, right? So all of these statements are somehow artificial, because some of the things that you think, let's say, are let's say a solid can actually be fluid. So for example, asphalt, glass, and plastic are normally considered solids, but over a long time interval they tend to flow like liquids. Okay, so especially with the glass, there's a big problem in Europe, where they have those cathedrals and they have those big window glasses and things like that, and they are, over this, several hundreds of years, they start flowing down. So let's say the window, instead of having, let's say uniform thickness like this, now because it's being flowing because of gravity, right, kind of have a something like this. So it's much, thicker at the bottom and then thinner at the top. So, it's dangerous, and we have to, like, take care of that. All right. So then what we have here is this: most substances can be solid, liquid, or gas, or the combination of these states depending on the temperature and pressure. Okay. So, and we're going to be learning a lot of those, dependencies in the next several chapters. Okay. So more generally, the time it takes a particular substance to change its shape in response to an external force determines whether the substance is treated as a solid, liquid, or gas. That means anything that technically can flow will be then considered as a fluid. That means, I'm not necessarily, like, let's say something that you can see right in front of you, right? Let's say water is flowing, you can see that, all right, so it's a fluid. But also that something like a glass or asphalt that can be flowing over time, so we can still technically consider those substances as fluid. All right, so the fluid is a collection of molecules that are randomly arranged and held together by weak cohesive forces and by forces exerted by the walls of a container. So technically anything that can, have some kind of literal force keeping them together, but, not strong enough to keep its shape, and they can flow. And liquids and gases are perfect examples of that. And so then we can, classify both liquids and a gas as fluid. Okay, again, something that eventually can flow. So in this chapter, we will be studying about fluid mechanics, but still, fluid mechanics is a very complicated concept. And let's say, though our class is not for engineering majors, right? But there are engineers who would, if they are going into that, let's say, branch of engineering, they're gonna have to take entire class on fluid dynamics. So because there could be so many parameters and variables and things like that that come into play. So since this is just a, introduction to fluid mechanics, and we're just going to be considering, let's say, the surface of the concept, we will be using a lot of simplifications. So, and then here are some of the simplification we're going to be making. So we're going to assume that we are dealing with simplified model of the fluids. So then the fluid is non-viscous. That means, let's say if the fluid is flowing, then all the parts are flowing together. about the same, basically with the same speed. For example, like a syrup or a honey or something like that, those are viscous. So if you know, let's say if there's an incline, and let's say if it's a honey flowing, right, or a syrup, the bottom actually moving slower than the top because of the interaction with the surface, with the friction and things like that. So that's basically, you know, makes our life a lot more complicated because you have now different layers and things like that. But if it's non-viscous, then it can basically more or less flow at the same, uh, rate, and do not sustain shearing forces. That means we can assume that basically there's no sort of like a breaking point for the fluid that we're considering. The only type of force that can exist in a fluid is one that is perpendicular to the surface. So let's say if you consider like a cube inside this container with the liquid, so the only force is basically the water molecules acting on this, perpendicular to the surface forces. Okay, same way we can think of, like, let's say if there's a molecule moving and colliding with this area A of a container, then it exerts a perpendicular to that force, right? Because if something is moving with some velocity, hitting a wall, it's going to exert a force on a wall, and that's also perpendicular force, and that's basically the forces, those type of forces that we will be considering. No drag forces, no, let's say, resistive forces, because if it's viscous, then there are also some other, more complicated forces, like, viscosity force and like a drag force or thing like that. So we will be not, considering those, simply to make our model simpler for us to understand. Um, so in terms of, as I mentioned, right? So let's say that there are air molecules inside, let's say, a container, or water molecules inside the container. They can basically be moving. Even when you look at the water and they're just sitting there still, right? Let's say in a glass, the molecules are actually in motion, and they always move around. So like, let's say here's a container, and let's say it is, you know, it has some water in it, right? And even though you just look at it, it seems like the water itself, right, at the macroscopic level, just sitting there at rest. Well, all the molecules inside are moving with some velocity. So the water molecules, right, inside, moving randomly with some velocity. And then you can think of, like, let's say if I take one molecule and think of, like, okay, so this guy is moving with some velocity v, it will be then moving and then hitting the container wall, and then basically bouncing back, hitting another container wall, like let's say something like this and something like that. So basically it constantly collides with the container wall. And in a way, each collision, right, results in the reversal of the component of the velocity vector of the molecule perpendicular to the surface. Okay. Now, we learn about, remember, impulse momentum theorem, right? We know that if there's a molecule coming and hitting the wall exerts a force. So the momentum is changed because, thing like this. If it's moving with the velocity to the right, hits the container wall, there's a force acting on it, which is a reaction force of the same force that molecule exerts on the wall. Then the molecule will be moving in opposite direction. Clearly, there is a change in momentum, right? Because momentum is to the right. Now momentum final is to the left. So there's a change in momentum because of this impulse force. Okay, but again, this impulse force is the reaction force, right, that molecule exerts on a wall. So molecule hits the wall at some surface area, right? And then we can assume that, if you have, like, let's say, a large number of molecules and then colliding with the wall, and then even just a tiny, let's say, element, or let's say the surface that, A, that you choose of the wall of the container, it's getting basically bombarded, constantly by the water molecules. And that is something that we're going to be done using. That means the forces they exert on that, let's say, sample area A, as a function of time, by constantly coming and hitting that area A, bombarding it with some, force, so that force, right, spread out over the area of the surface, is what we call pressure. So the pressure is basically nothing but a force per unit area. So again, if you have a container and there's a molecule moving with some velocity v, right? When it hits the container wall, I can choose like small area, or I can maybe, like, let's say, let me use a different color so you guys can see, right? So let's say I'm choosing this area A of interest, and then I'm saying, okay, so here's the A of that, area of that, like a small sample, right? The area of the container wall. And then as the particle 1, 2, 3, 4, 5, hundreds of particles colliding with the wall, at this area A, then this total force acting at that, area of interest, that ratio is then defined as the pressure. That means they exert pressure at that area. Okay. So the pressure is defined as force per unit area. The units are newtons per square meters, right? Because force is in newtons, area in meters square, but that's not quite the SI unit for the pressure. So the SI unit for the pressure, we define that ratio to be equals to Pascal. That means when the molecule hits with the 1 Newton force at the 1 square meter area, then that pressure is equals to 1 Pascal. All right, so Pascal is the SI unit for the pressure. And one of the things we're going to see here is the pressure is one of those things that it has many, many, different units. There's a Pascal, there is a Newton per square meter, there's a PSI, there's millimeter of mercury, there's a ATM, all those things. But, obviously one unit that we want to work with, to be consistent, right, is the Pascal. The Pascal is the SI unit. So most of my calculation and everything should be done in terms of Pascal. All right. So another thing, obviously, part of what we call fluid is also air molecules, right? So that was water molecules, but we also have air molecules, and air molecules also are moving and colliding. So let's say if this is Earth or the surface of Earth, and there's air molecules like this, and they constantly collide, let's say, with the surface. And then when they collide with the surface, they exert force. Basically, you can think like all that air molecules above, right? Basically pushing down. And when the air molecules are colliding with the, let's say with the surface, or basically colliding with each other and things like that, so then you can say that there's a force acting at the surface. So we can then calculate the atmospheric pressure at more or less at the sea level, right? And then as we can assume that there's a collision between them, so then we can look at in terms of pressure as we go above the surface. And generally the pressure as we go above the surface will be decreasing, and it will be decreasing because the pressure is due to the air molecules, and air molecule concentration is decreases with the altitude. So higher you go, less air molecules, smaller the pressure, until you eventually, let's say, reach space where the pressure here equals to zero. There's no pressure in space because there are no air molecules, right? So, and you can say that at the the from the sea level or the surface, as you go in terms of like your altitude, right, then pressure, as you increase your altitude, the pressure basically decreases. We can calculate that pressure at the sea level from the from the atmosphere, right? What we call air molecules, like atmosphere, right? And that atmospheric pressure is like P0, right? That's what we use for the atmospheric pressure, is defined as 1 atm, but atm is specifically when you talk about, let's say, atmospheric pressure at the sea level. But obviously atm is not a SI unit, so we have a conversion factor where 1 atm is roughly 101,000 pascal. So it's 1.013 times 10 to the 5 pascal. That means 1 atm is roughly 100,000 or 101,000 pascal. Okay, so sometimes it's easier to use ATM as a unit. Sometimes it's easier to use Pascal. So there will be some problems where you might see, especially in the chapters 16 and 17, where maybe using ATM is a little bit more appropriate. But more or less in this chapter and most of the time when we can, using SI unit is the most appropriate way of writing the pressure. All right. So as I mentioned, right, the pressure decreases, the the atmospheric pressure decreases with altitude. But, or we can think of it like this: if you start from space where the pressure is zero, then as you're going down toward Earth, then pressure is increases, right? As you go down, pressure increases. How about, let's say this is not a solid surface, but for example, I don't know, sea level, or this is a sea, or like an ocean or something like that, right? So how about the pressure there if you continue going into the sea or into the ocean? Well, the pressure will be increasing with depth, because sort of like a similar way as the pressure increases as you go from space toward Earth because of the concentration of their molecules increases. Same way as you go down, well, then you have not only the air molecules, but you also have the water molecules. If you go down, there are more concentration of water molecules, and then pressure actually increases with depth. Again, as in terms of as the delta Y goes down, right? Or let's say, maybe we can use H for that, pressure will be increasing. So we're going to be able to derive an equation in terms of how to calculate pressure somewhere over here, somewhere over there, right? But the idea here is generally that the pressure in the sea or a lake increases the deeper you go, and atmospheric pressure decreases with increasing altitude. So if your reference is basically space, then as you go down, toward Earth, it's basically pressure increases all the way. Okay. All right, so here's then what we're going to do. So we're going to basically find a model or a sample where we're going to be then developing the equation for the pressure at some depth H. So we're going to take, for example, a fluid that is at rest in a container. All portions of the fluid must be in static equilibrium. So in a way, what we're studying in this chapter is the hydrostatic equilibrium. So one of the things you will notice that, this chapter has two parts. One is the hydrostatic equilibrium, which means the fluids are at rest. The second part is the moving fluids. I don't really go into moving fluids. I only cover this portion right now. This for this part is going to be in terms of the hydrostatic equilibrium. And what I have here is we're going to assume that always when we're dealing with the fluid, in this part, right, it is in equilibrium. It's in static equilibrium. Okay. So all points at the same depth must be at the same pressure. Otherwise, the fluid would not be in equilibrium. So let's say we have this. So you have a container with, some, a liquid, right? Basically, just generalizing, let's call it fluid, sitting there in static equilibrium. And the container is open to atmosphere. That means, in a way, there are also, like let's say we have a, gas above it, right? So that's why it's a fluid. It's a combination of, let's say, combination of the air molecules and the water molecules, combination of liquid and gas. One of the things we do here is we use rho to represent a density, and this is going to be density for, let's say, the liquid that we're using. Because, for example, one of the things I want to know here is what is the pressure at the different depth of inside this liquid. So let's say then this density is for the fluid, let me put like fluid. And if you remember, the density equation is defined as mass per unit volume, mass per unit volume. And this equation actually going to be used quite a lot because, in this and even the next few chapters, right, this equation always going to be used to a lot of times eliminate mass and represent mass as a product of density times volume, right? Because if the density is mass per volume, then mass is density times volume. So a lot of times we're going to see that that product of density times volume will replace the mass. All right. So now imagine that we have this container with some water, and what we're going to do here is we're going to take a sample, like a imaginary parcel of water. So let's say this is my sample, okay, and this sample now can be like this, or can go all the way to the surface, for example. But what I'm going to do, I'm going to take it all the way to the surface. Easier to derive the equations like this and be able to see. And what I have here is this then. This particular parcel of water, let's say the surface area A above, let's call this A1, because let's call this 0.1. And then it also the surface area here at the bottom, let's call this 0.2. So then this is basically area 2. Okay. Now, think like this. So this column of water has mass M. This is mass of the fluid. When I say mass of the fluid, this is basically the mass of this imaginary sample of water that I'm considering. Okay, so basically, which is a cylindrical shape. Now, what I'm going to do here is this. I'm going to look at sort of like, let's say, the forces acting on it. And I can see that there are 3 forces acting on it right now. One is from above at 0.1. So this is the atmospheric force. That means that surface, right, that surface A1, all the air molecules, right, all the air molecules above that surface bombarding you with the atmospheric pressure basically. But let's call this, there's a force Fa, or technically I can say F0 because that's what we use for the atmosphere. So F0 is the atmospheric pressure. Also, what I have is this column of water. Well, it has mass, as I said, right? So then the gravity acting at its center of mass. So I can say there's a center of mass, and then the gravity acting on it, right? So there's then the gravitational force. Okay. And well, think like this: so that if that parcel of water, that this the sample of water just sitting there with two downward forces acting on it, but it's in static equilibrium. That means there has to be another force acting in the opposite direction, and that's this force over here. And this is then the force that water molecules, at the bottom, exerting, force at the, surface A2. That means in a way, what I have here is there is basically the net force, which is the gravitational force plus the atmospheric force plus force at that depth d, and this is equals to 0, right? Basically, this is just a general net force equation, vector sum of the forces. But I can see that these are or vertical, where then this force at depth d is positive because it's up, let's say j hat, and then the gravitational force is negative j hat, and then this atmospheric force is also negative j hat. That means, and their sum is equals to 0 because still that sample of water just sitting there in equilibrium. Okay. Now, what we have here is then this again. So we have three forces acting on this, imaginary cylindrical parcel of water that I have. Okay. So, and what I can say here is then this net force. Again, let me write that down, right? So this net force is the force of that D minus atmospheric force minus then gravitational force. They're all, vertical, right? So, and then this equals to 0, which means that, I can, at this point, look at, instead of the force, I can look at basically the pressure they exert at those two areas by remembering that pressure is force per area. That means I can rearrange and write the force as the pressure times area. So force is pressure times area. By the way, it's generally like a capital P rather than lowercase p. Lowercase p mostly like for the momentum, but sometimes I write it as lowercase p, the same thing. So this is basically the pressure. All right, so that means I can take this f of d and replace it at the pressure, the depth times area 2 minus this f of 0, which is atmospheric pressure. This is atmospheric pressure, right, times area 1. Because remember, this was 0.1, this was 0.2. And then minus f of g, which is the gravitational force. I can just write as mass of the fluid times g, and this is equals to 0. Okay. So that's kind of what we have. So there's a downward atmospheric, force, which I can write as pressure times area. Then upward, force from the water molecules at that, surface area 2. So I can write as, P times A. I just write P D, which is P at pressure at that depth D. And then downward gravitational force mg. Okay. That means what we have here is this PA minus P naught times A minus mg. Okay. So then the mass of the liquid, this is, as I said, right? So we take the mass of the liquid and we rearrange and write it as density times volume. So that means, if I have this, that was my column of water, right? Remember, its mass is then can be replaced with density times volume. Now the volume, since this was the, surface area A and this is height H, then the volume of a cylinder, remember, is area times height, A times H. That means I can take this volume times density and say that this is equals to volume, which is A times H, then times density. Actually, density is missing from there. So A times H times density. Okay, that means mg, this term, becomes rho GAH, because rho AH, that's the density times the volume, right? Then times G. All right. which means I can say then PA is equals to P0 times A plus mg, or P0 times A plus rho g A times H. From where you can see that I can go ahead and cancel all the A's, right? I can cancel all the A's like you can see over here, right? And then have final equation where if I have a container, and this is basically the, the container is open to atmosphere, and this is being the surface, at any depth H, right? Let's say if I want to consider below the surface, then I can find the pressure at that position, which is then again depth H below the surface, as pressure there is equals to atmospheric pressure, because it's open to air molecules, right? That means the surface is bombarded by atmospheric pressure, then plus density of the fluid times 9.8 times the height that we're considering, which means that the pressure will increase, greater my H. That means deeper I go, greater than this atmospheric pressure, greater this pressure, that depth. All right. So if the fluid is open to the atmosphere, as I mentioned, right, so P0 is the pressure at the surface of the liquid. Then, you have to include that in equation. Then P0 is the atmospheric pressure, 1 atm, or roughly 101,000 pascal. The pressure depends only on the depth H within the liquid. And also, one thing you can see here, if I choose some point P over, some point P over here, or some point over there, as long as it's, along the horizontal line with respect to that original point H that I considered, then I'm going to get same pressure, because then, same H, for both, all 3 points, right? That means along this horizontal line, they all have the exactly same pressure. Now, so then that's why the pressure depends only on the depth H, and the pressure is the same on all points having the same depth, independent of the shape of the container. Now, what does it mean? It means, for example, if instead of a container like this, I have something like that, let's say. Let's say something like that, I don't know. So, and let's say if I pour water into this container, so if they're connected, they're gonna get the same level, they get to same level. And for example, if I measure the pressure here at point 1, using basically that equation, right? Pressure at point 1 is equals to atmospheric pressure plus rho g times H. This is being the H. Then, for example, then I know pressure everywhere along this horizontal line, including, let's say, this point 2, because point 2, pressure is exactly the same as point 1 because it has exactly same height from the, let's say, surface, or even if this guy was close and isolated, it still would have been exactly same pressure. Okay, so sometimes we use this with the instrument where we might have a, let's say, another container with different fluids and things like that, so then I can find the pressure over here, right, and things like that. So that means what I can do here is pressure is the same at all points, having the same depth, independent of the shape of the container. So sometimes you might have like a U shape like this. Okay, so and let's say I can find the pressure here. Again, that means it's the same pressure as over here. So that, independent of its shape, right, you can always get the same pressure as long as the same depth. And here's an example of using the simulation that we can see in terms of let's say, okay, so something like this. See, let's say we can have different shapes, and you can see, right, the shape is such that if, as long as they're connected, that the water level is going to be the same. So for example, if I pour it out, and if you do see, they're going to always reach the same level, even if there's something like this. Okay. All right. So let's see this. So let's say this one, allows me to, in a metric system, right? So measure the pressure. So let's say if I take it, see, pressure here is like 101.3 kilopascal. 101.3. If as I go up a little bit, say decreases. So I go down a little bit, increase all the way to the water, right? It's basically 101.2. But as I go down, so now see, pressure increases. And this is like only like 1 meter, 2 meters, and then 3 meters, right? You can see already increased by about 20% almost, something like that. So the water basically increases. Also, the pressure then depends on, let's say, remember, so this is, let me write it here. Pressure is equals to atmospheric pressure plus rho fluid G times H. Okay, that means this is, let's say, assuming that this is water, and water has a density of 1,000 kilogram per cubic meters. Okay, so which you can see over here, right? So on the right side, so here we have the pressure, sorry, the density of the fluid, in which is 1,000 kilograms. This is water. Now, one thing I can see here is, you can see, right, if I go to the gasoline, that means I have to decrease. Honey is actually increases. And one thing I can see here is, for example, right now, if it's water, exactly, let's say 2 meters below the surface, it is 116.5 kilopascal. But if, for example, I go and have more dense fluid, then see it increases the pressure. If I have less dense fluid, it decreases the pressure. Okay, because of this rho, the density, right, in the pressure equation, it's pretty much proportional to that as well. So, it decreases with, let's say, dense fluid density increases with the increases and decreases with the fluid density. And also obviously gravity, right? So if you're on the moon, for example, and things like that, right? So let's say your pressure decreases if you're on a, Jupiter, for example. I guess this is Mars, 3.7 meter per second square, and this is Jupiter. You can see, right, it's much, much higher pressure. So compared to, let's say, Earth. Okay. There you go. Yeah, so something like this. And it can be even used sort of like, let's say, to find, for example, what type of, let's say, substance this is. So let's say if I go 2 meters below, and this is the pressure that I'm getting, then I can use this equation to calculate the density, right? Because the pressure is, let's say, 101.521 kilopascal, and this is equal to atmospheric pressure, which is 101.3 kilopascal. Then plus, rho, which is unknown and we want to find, right? But then times 9.8 times and 2 meters. That means we have everything but this unknown density, and we can just rearrange it and solve for that. Okay, so then you can look at it in terms of fluid A and C and B and things like that. So it's a nice simulation, right, that I will upload. You guys can, play with that and, work with that. Right. So also you can do in terms of the English, or, like you can write in English, it's PSI, atmospheric unit, or the metric, which is in Pascal. All right. So we also have that change in pressure at the surface must be transmitted to every other point in fluid. And this is known as Pascal's law of Pascal's principle. So this is one of those things where variation in pressure with depth, right? So that means, for example, you have a closed container and you apply pressure somewhere. If it's a closed container, right, then this pressure can be transmitted everywhere. And this is generally used for, let's say, an application like hydraulic lift or something like that. For example, so by the way, let me read the Pascal's law. It says the change in the pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. So this is a nice, law that can be used to, for example, in hydraulic lift. So think like this. Here you have a, let's say, a large surface area where you can maybe, like, let's say, put a car. Okay, so let's say this is our car. And this is basically sitting at the, let's say, top of something that has a fluid in it. And then this is connected to another area. This is like, let's say, another area. Let's call this area 2 over here. And this was an area 1. Okay. And then inside is some kind of fluid. And it's enclosed. So that means it's closed. But these guys are sort of like a piston. So there's a piston over here that can make it move up and down. So then one of the things we can get here is this. Because it's enclosed, then pressure is the same everywhere. That means P, let's say at area 1, let's say P at area 2, right, are exactly the same. Pressure 1 equals pressure 2. Now, what is pressure? Well, it's force 1 over area 1. How about pressure 2? Well, it's force 2 over area 2, right? And one of the things we can do here, then we can see that since this is true, I can actually have this force 1 as input force, right? So force 1, so like let's say F input. And if I can basically, because of the difference in areas, I can apply just a liberal force where then the force here output, where force 2 is force output, can be much, much greater if I can, let's say, have this entire thing is enclosed. We have basically a fluid, enclosed fluid. And if I apply pressure, it transmits everywhere. And if I use the, let's say, the right amount of the proportionality of the areas, I can get as much output force as I want in terms of, like, let's say I can maximize, I can double, triple, make it 10 times and so on and so forth. Because again, pressure 1 equals pressure 2, which means this ratio of F1 over A1 equals to the ratio of F2 over A2. So if I rearrange, then F2 is equals to A2 over A1 times F1. So for example, let's say A2 is 10 times A1. So like, let's say, look at it, right? So this is my area 1, this is my then area 2. It's about 10 times more. And let's say I apply, let's say 100 Newton force at point, at the area 1. Then this becomes 10 times area 1, which is area 2, divided by area 1, then times 100 newtons. See, this cancels out. Then my output force, which is F2, is then equals to 1,000 newtons. So I made the output force 10 times bigger. What if technically this is way more than 10 times? So what if this is 100 times bigger? That means area 2 is 100 times bigger than area 1. Then this becomes 100. So then this becomes, let's say, then 10,000 newtons, probably good enough to lift a car. That means we just apply liberal force over here, and then the entire car is lifted. So that's what a lot of mechanics do, right? So they have this devices where they can just press on, on something that, with their foot, right? And then the car is basically lifted because all they do is just use this Pascal's law. They apply pressure at one end, and it is, enclosed fluid in the entire place, right? And then this fluid transmits the pressure, but because area 2 is much bigger than area 1, then you apply enough force that can basically lift a car. All right. Another thing in this chapter that we're going to be considering, pretty much still we remember we are talking about hydrostatic equilibrium, is a buoyant force. And this is a new force. So this is a new type of force that we haven't talked about before. And this is an upward force always exerted by a fluid on any immersed object. Okay. So think like this, when you take a beach ball, right? Let's say at the pool or, I don't know, like an ocean or something like that. And you take the beach ball and push it down into the water. See, when you let go, you might think that it's just going to continue falling down, right? Because you've been pushing it down. But in a pool, right? If you take the beach ball, push it down into the water, you let go, the beach ball is basically pushed upward. What pushes it upward, or what's responsible, is this buoyant force. It's the upward force exerted by a fluid on any immersed object. It is technically acting both in liquid and gas, right? So for example, balloons and things like that experience buoyant force in air, but it's much, much, stronger, this force, obviously in liquid because of the water molecules, right? Much, let's say, bigger and, let's say heavier and much more, let's say, compared to the air molecules. Okay, right? Imagine a beach ball sized parcel of water beneath the water surface. Because this parcel is in equilibrium, there must be an upward force that balances the downward force. So that means what we have here is, so let's say over here, right? So this beach ball over here, thing like this. So let's say that you put the beach ball there. So there are two forces acting on the beach ball. There's a gravitational force, and then there's a buoyant force. Okay. So that means, if you just barely holding the beach ball, it is not going down, even though the gravity is acting on it, right? So let's say if there was no liquid but air, the beach ball just will fall down because you're not really holding it, but just basically barely touching it. But in liquid, right, it's just gonna stay there because there's gravity pulling it down, but then there's buoyant force pushing it upward. And let's say right now we can say that in terms of is it gonna go up and float or go down and sink, depends on, basically the magnitude of this buoyant force compared to the gravitational force. If the buoyant force is stronger, the beach ball is going to be pushed upward and starts floating. If the gravitational force is stronger, then it's going to basically pull down and go and sink. That means that the net force applied by the fluid surrounding the beach ball is the same right now as the gravitational force. All right, so now this is basically this in terms of then, okay, so this buoyant force, right, is, even though we call it a force, and remember the Isaac Newton is basically one of the first one who came up with this concept of force, but this idea of this buoyant force, right, or just this buoyancy, right, it's been around for a very long time, and from the time of Archimedes, and Archimedes been around for a long time. I think he lived in a Greek city Syracuse about 2,500 years ago, and he is the one who actually um, developed some of the initial let's say properties of this buoyancy, right? So, and here's his principle. So the magnitude of the buoyant force on an object always equals the weight of the fluid displaced by the object. Now, what does it mean? So again, obviously, the Archimedes didn't put it in the form of force and things like that, but the idea here is this. So this buoyant force is equals to the weight of the fluid displaced by the object. All right. Well, so what this means is basically that if I come back over here, for example, and I kind of redo this experiment. So think like this. Here's a water, and this is the water level. Now, when I submerge this beach ball into the water, right? When I submerge this into the water, I'm sure you have seen this effect. As soon as you submerge something into the water level goes up. That means as soon as I submerge that beach ball into the water level will go up. Now this is then what I call displaced fluid. Okay, so that's the displaced fluid. That means that's the amount of fluid that has been displaced by the presence of the beach ball. And one thing we have here is then the buoyant force is equals to the weight of this displaced fluid. Let me put like DFL, displaced fluid. So it's equal to the weight of this displaced fluid. That means if I collect all that water that has been displaced, I put it on a scale and find its mass, then so times 9.8, that's buoyant force. The magnitude of the buoyant force equals to the weight of the displaced fluid, which is basically equal to the mass of the displaced fluid times G. But the way we write buoyant force generally is this. So the magnitude of the buoyant force is basically, and remember, it's always J hat, right, upward. So the magnitude is, again, mass of the displaced fluid times G. Usually what we do in this chapter, as I mentioned, we take the mass and we replace with the density times volume. That means this is then equals to density of the fluid times volume of the displaced fluid, then times G. Okay, so I'm kind of like run out of room, but that's kind of like what I have. So if I come back here, so then I can write down that magnitude of the buoyant force is equal to the weight of the displaced fluid, which is then mass of the displaced fluid times G, then replace mass with the density of fluid times volume of the displaced fluid times G. That means the volume is only for that displaced fluid, right? That means what I have here is this. When I submerge this beach ball, the water level goes up by that much, and the volume of that by how much is displaced, right? So this is what goes over there, not the volume of the container, but how much volume of that water level went up and things like that. All right, so now what Archimedes basically discovered, which was something I'm going to talk about again in a little bit, was basically this. Water level that goes up, and if I measure the volume of the water that has been displaced, so volume of displaced fluid, it will always be equal to the volume of the object. That means how much volume of water will be displaced depends on the volume of the object. For example, this is a beach ball, And let's say beach ball has, I don't know, let's say 200 cubic meters volume. And let's say, I don't know, like let's say 1 kilogram, probably too much, but let's say this is 1 kilogram beach ball has a 200 cubic meter volume. Then I'm going to replace it with a bowling ball with the same, let's say same volume, but obviously bowling ball is like, I don't know, like let's say 20 kilograms or maybe even more than that, right? So, but let's say it's 20 kilogram bowling ball and with the same volume. The question is, will the water level, how much it will displaced? Will it be more than before or less or the same? Remember, I'm replacing a very light beach ball with a bowling ball, much heavier bowling ball. But the bowling ball has exactly same area, same volume as the beach ball. Well, interestingly enough, how much water will be displaced is the same as before because it only depends on the volume and not the weight or not the mass of the object itself. That means how much water is being displaced always equals to the volume of the object. Because if you go back over here and you can see, right, what it does, let's say, see, this is the beach ball, right? So this is the size of the beach ball. And now beach ball occupying the space of all this water that was there before it. That means if you push the beach ball into the water, then it basically pushes water where the volume of the water equivalent to this, the space it occupies now. So that's why how much water level will go up exactly equals to this, volume of the object itself, regardless of its size. That means regardless of its mass, like heaviness. And this is a very important thing that basically the Archimedes figured out. Okay, with the beach ball underwater, the buoyant force equals to the weight of the beach ball sized parcel of water, not weight of the beach ball, but beach ball sized parcel of water, and is much larger than the weight of the beach ball. That's why the beach ball can be pushed upward, right? Remember, this is the beach ball. Then there's a buoyant force and there's a gravitational force. And what we'll have is the beach ball will be larger, so it's going to be pushed upward, right? Beach ball always pushed upward, which means beach ball, it has a greater buoyant force than the gravitational force. Okay, that means the weight of that displaced water is greater than the weight of the beach ball itself. Okay, so that's why what we get here is we get the greater net upward force, and the beach ball is pulled upward and it starts floating. Okay, now then we're going to start developing things, which, I already gave you some of them. So similar way, right? So instead of a beach ball, let's consider a cube immersed in a liquid. And the idea here is this. So there are, also a few other ways we can look at it in terms of the beach ball, the buoyant force. So think like this. So if you put the object inside the water, you have two forces, buoyant force and then the gravitational force. And then basically you get a tug of war, right, between those two. Okay. So then if you then calculate or basically rearrange, so this is the equation that I gave you already, right? So the buoyant force is equals to the density of the fluid. Let's say if it's water, it's 1,000 kilogram per cubic meters times 9.8, but then times the volume of the displaced fluid, which Archimedes also figured out that it's equals to the volume of the object. So I'm putting, I guess, DISP, right? This is displaced. So I can just put it like this. So this is volume of the displaced fluid. Okay. And it's always going to be equal to the volume of the object. Okay. Now, when the object is then submerged, you basically have this, right? So you have F, like this. So let's say here's a container. Let's say this was your object. Remember, you have then the gravitational force acting down and then the buoyant force acting upward. So then you have basically B minus F of G equals, let's say, I don't want to put 0. Let's say if it's equals to 0 if the object is at rest, like let's say, but equals to something. Now that something basically will determine if the object is going to float or sink. Because what I have here is in this equation, I have buoyant force minus gravitational force. Remember, buoyant force equals density of the fluids times G times volume of the displaced fluid. Okay, but see, I can replace this volume of the displaced fluid with the volume of the object because, as I say, they are equal to one another. But let's do this first. So this is Density of the fluid times G times the volume of the displaced fluid. Then minus mass of the object times G, right? Because F of G is mass of the object times G. And then what I'm going to do here is this. Density of the fluid times G. I'm going to replace this with the volume of the object because it's the same. Then minus, then mass of the object going to be replaced with density of the object times volume of the object. Remember, we always like to replace mass with the density times volume. So it becomes, mass of the object is replaced with density of the object times volume of the object, then times G, which is my net force. That means what will happen on the right side, which is mass times acceleration. That means what will happen on the right side depends on this, let's say difference in the left side. And you can see, right now, I have the same G for both, same VO for both. So I can take out G, VO, and all I have is the density of the fluid minus density of the object equals, whatever it is. And that's what we have. See, this difference, right? Buoyant force minus gravitational force at the end of the day end up being just a tug of war between the densities of the object and, let's say, the fluid. That's why will the object sink or float or just sit there? Depends on this difference. Raw fluid minus raw object. If the raw fluid equals to the raw object, then this is zero. So then that means, this whole thing is zero. That means mass times acceleration is also zero. Object is in equilibrium. But if the density of the object is less than density of the fluid, like wood or a plastic or a beach ball, right? They have less density than water. Then the buoyant force is stronger, right? You can see, right? So basically what I had is this. I had volume of the object, G, and times density of fluid minus density of the object. And this is equals to then, let's say, mass times acceleration, for example. So if I have this, it means buoyant force is greater than the gravitational force if the density of the object is less than density of the fluid. That means this term is bigger than this, right? So then you have buoyant force that is greater than gravitational force. So then B minus F of G is equals to mass times acceleration, and acceleration is positive. So that means it accelerates upward. That means the object is less dense than water. So buoyant force is going to be greater. Or you can have the object with the density that is greater than of water, like, I don't know, a rock or aluminum or iron or something like that, much more dense, and then it will be other way around. Then the density of object greater than the density of the fluid. So B minus F of G, in this case, B is less than F of G. Then this is equals to mass times negative acceleration. So you're going to get a negative acceleration. Okay. So the object will then go and sink. And this is basically what we get. This is assuming that you have a fully submerged object, right? And that's the equation that basically you're using. So then that's why you have to look at it in terms of, is my object more dense than water or not? All right. Change a little bit. Let's say if you have partially submerged object, right? Because if it's partially submerged, only parts of it inside water, and only that part that is inside water is displacing, let's say some kind of fluid. So that's right. So if it's partially submerged, then upward buoyant force is balanced by the downward gravity. That means, they are equal to one another because the system is in equilibrium, right? It's just floating there. So the buoyant force equals, F of G. And in this case, so the volume of the fluid displaced is not equal to the volume of the object, because not entire object, you can see, right, is in the liquid. Not entire object is in the liquid, so the volume that is displaced not equal to the volume of the object. So then one thing we can do, we can use a ratio, because only fraction of the volume of a floating object is below the fluid surface. So we can say that volume of the displaced fluid over volume of the object equals, and the density of the object over density of the fluid, for example, and I can use this to find volume of the displaced, fluid, which will be density of the object over density of the fluid, then times volume of the object. So you can see, right, they are not equal to one another. So this ratio will tell you that, what will be the displaced fluid. Okay. So this is the equation for the partially submerged object. All right, so let's look at an example here. We want to calculate the absolute pressure at an ocean depth of 1,000 meters. Assume the density of seawater is actually slightly higher than the fresh water, is 1,030 kilogram per cubic meter, and most of the time you can actually use 1,000 kilogram per cubic meter for the seawater as well, because it's very, very tiny difference. All right, so the air above exerts a pressure of 101.3 kilopascal. So we want to find this at this depth 1,000 meter. Well, we know then for part A, pressure depth D or H, right, is just atmospheric pressure plus rho GH. Okay, so this is then 101,300 pascal, then plus density 1030 kilogram per cubic meters, then times 9.8, then times 1,000 meters. Okay. Then the pressure will be 1.02 times 10 to the 7 pascal, or basically, well, we'll be seeing, as you can see, right? So this is about roughly 10 times greater than the atmospheric pressure. That means you go 1,000 meters below the surface of the ocean, and well, never mind. So this is actually, if I'm doing in terms of, remember, the atmospheric pressure is roughly 10 to the 5 pascal. And this is 10 to the 7 pascal. That means it's 100 times, right? 100 times stronger pressure than atmospheric pressure. That means 1,000 meters below the ocean, you're going to get 100 times stronger pressure. And this is the reason that, let's say, you can't really dive too deep, because when you're diving, the pressure from outside is basically 100 times greater than pressure inside. Because remember, you are breathing that air, right? Inside your body is the atmospheric pressure, it's air molecules. So then atmospheric pressure inside your body, let's say 10 to the 7 pascal outside of your body, then you get basically pressure from outside trying to crush you, pressure from inside trying to prevent it. But if you have 100 times stronger pressure from outside, yeah, they're going to do a lot of damage, right? So that's why you can't really dive too deep, or even submarines and things like that, they can't really, right? Because again, inside the submarine, you have air molecules, right? Atmospheric pressure, and outside you have, the water pressure, right? And this is, if it's much larger, right, then this inward, right, collapsing force is much stronger, so that can, basically sink the submarine. Part B says, at this depth, what is the buoyant force on a spherical submarine having a diameter of 5 meters? So let's say if you have a diameter, so this is part B, of 5 meters, that means then there's a radius of 2.5 meters. Then that means I can calculate the area for this to be, for example, pi r square. But, remember, technically what I need here is the volume, and the volume equation is for third pi r cube. Okay, basically in terms of this, because this is a spherical. So actually the area of the sphere is not pi r square, is 4 pi r square, by the way. All right, so in any case, so here's the buoyant force. Remember, this is equal to density of the fluid times G, then times volume of the fluid that is, this spherical submarine would, let's display, but let's say it's equal to the also volume of the object. So then 1,030 kilogram per cubic meters, then times 9.8, then times this 4/3 pi 2.5 meters cubed. And if I get that, then buoyant force will be 6.61 times 10 to the 5 pascal. Sorry, this is buoyant force, Newton. There you go. So that's the buoyant force. All right, so here's another example. And this is, one of those, something I was talking about in terms of like Archimedes. So there's a legend where Archimedes, basically the way he figured out, this Archimedes principle was that he was living in a Greek city, Syracuse, and the king of the city wanted to have, just like any other kings, right, I guess, wanted to have, like, let's say, this crown of pure gold. So he hired someone, gave him all this gold, and said, okay, go make me a crown of pure gold. So, and let's say here's the crown, right? So the guy made the crown, gave it to the king. King, was happy initially, was wearing the crown, but then he got suspicious. It was like, what if this is not of pure gold, right? What if the crown is not pure gold, and the guy cheated and took out some of the gold, replaced it with the cheap metals and things like that? So how would I know? How would I, let's say, see if this is pure gold or not? So then he tasked, Archimedes with that problem, right? Go ahead and figure out if the crown is pure gold or not. And obviously, one of the things we have here is there are like several ways, we can do this. So for example, that one legend, and there's like a number of ways, different versions of this legend. So think like this. The idea here is that we know that, let's say, if you have an object, you find its mass, you find its volume, then you can take mass over volume, and that's going to give you density, right? And then this density will then tell you if the object is gold or not, because let's say they know the density of the gold, or they know this ratio value, because they can take a one small piece of gold that's easy to measure the volume and mass. So if they do mass over volume of this small piece and find that the ratio, which we call density, right, they can compare to the crown, mass and crown volume ratio, and then see if they're the same or not. Well, it's easy to find the mass of this, let's say this crown, but how are you going to find the volume of that crown? It's very unusual, shape. Well, it's unusual shape, so you can't really find its volume accurately, and that was, the problem with Archimedes. He was having a hard time figuring out how to get the actual volume of the crown, until one day he was basically taking a bath, and he filled out the bathtub with water, got into the water, and then he realized one thing, that basically when you go into the water level goes up, and that directly linked to his, basically his own volume. That means how much water level goes up directly related to his own size, right? Basically how much space he occupies. That means his volume. That means, water or display volume of the displaced fluid equals to the volume of the object. And that's when he basically, and he was obviously, taking a bath naked. He jumped naked and ran to the palace screaming Eureka. And that's what we have this title, right? So it says Eureka. That's basically means in Greek, I found it. So he was so happy that he ran naked to the palace to, tell the king that he found out, or he found the solution to the problem. Well, obviously, one of the things we can imagine is that the reason we know this legend is because, once he, did that, and it's not very difficult anymore to do, right? All you have to do here is um, take a container, have a water all the way to the brim, like this, and then have something that can collect that, displaced fluid, right? Let's say something like this, right? And then put the crown inside, whatever the shape of the crown is. Then it's gonna, you're gonna displace a certain amount of water, right? Then you can collect that. You can measure the volume of the water, and then you have volume of the object, because you have the volume of the displaced fluid, right? Which means the volume of the crown. Then you can do mass of the crown, or volume of the crown, and find the density. Okay, so that's the what he could easily then do once he figured out how to get the volume of the crown. Okay. Now, another way, kind of this legend goes is a little bit different here, but, let's look at this. So it says Archimedes supposedly was asked to determine whether a crown made for the king consisted of pure gold. According to legend, he solved this problem by weighing the crown first in air and then in water. Okay, maybe he did this way, maybe he did the other way that I, went over. But, the idea here is this. So this is like a little bit another way of finding the buoyant force. So suppose the scale read 7.84 newtons when the crown was in air, and 6.84 newtons when it was in water. Okay, that means, for example, if you take the crown here in air and then find its, let's say, thing like this. So this is in air, put it in a scale, and we get 7.84. Same thing we repeat, but, it's fully submerged in water. Well, the reading is 6.84, okay, which means it's slightly different, right? Well, that's because when it's in, let's say in air, the reading basically gives you the tension force, which is equal to the gravitational force. And there are only two forces. So this is in air. So you have the tension, and then you have gravity. And they're equal to one another. But when it's fully submerged in water, then you have tension force gravitational force, but also buoyant force. Okay, that means what we get here is the reading here is different because of that buoyant force. Now, the equation basically goes like this. So tension force plus buoyant force minus mg equals 0. Okay, and this is obviously, let's say T2, this is T1. Okay, now remember the reading here, right? The reading here for T1, which was 7.84 newtons. Remember, this T1 was equal to the F of G, right? That means F of G itself is 7.84 newtons. And then T2 here is now is 6.84 newtons. That means now I have T2 plus B minus mg, where I know the value of T2 and I know the value of Fmg, which is, F of G, right? So then I can find the buoyant, sorry. So I can find then the buoyant force from here by saying this is mg minus T2, which is basically 7.84 minus 6.84, which is nothing but 1 Newton. That means the buoyant force is then 1 Newton because it's the difference between actual weight, or T2 sometimes known as the apparent weight. So actual weight, which is 7.84, minus apparent weight, which is 6.84. Okay, now that's my buoyant force. But we also know one thing is that buoyant force is equal to then density of the fluid times G and times volume of the crown, let's say, for example. But this is basically because like the crown is our object, right? So from here I can basically say volume of the crown is equal to then the buoyant force divided by density of the fluid times G. Okay, then what I can do, I can remember then the equation for the density of the crown, which is mass of the crown divided by volume of the crown. So then this will be then replacing volume of the crown with that. So then this will be then mass of the crown divided by buoyant force over density of the fluid times G. So then this will be M crown G density of the fluid divided by buoyant force, where MC times G, right, mass of the crown times G is nothing but the weight of the crown, which is 7.84. That means density of the crown here is equals to 7.84 newtons times 1,000 kilogram per cubic meters for the density, then divided by the buoyant force, which was just 1 Newton. Then if we calculate, we're going to get 7.84 times 10 to the 3 kilogram per cubic meters. And that's the density of the crown, which is roughly 7,000, right? 7,800. That means the density of the crown is roughly 7,800 kilogram per cubic meter. Well, let me tell you the density of the gold. It is approximately 19.3, basically times 10 to the 3 kilogram per cubic meters. That means roughly 19,000 kilogram per cubic meter, but the crown was only, let's say, roughly 7 or 8,000. That means definitely the king was cheated, and he had a lot of gold was taken out and replaced with cheap metals. All right, so that's then complete this chapter, or this part.